Okay, if we skip to the end, sometimes that helps us when we read the word problem to cue up what we're supposed to do. We're supposed to find a rate that the height of the water changes at a particular point in time when the water is 3 meters deep. So we want to know the rate of change of the height. The rate of change of the height of the water with respect to time. Oh, I don't need that prime, it's redundant. dH dt. We want to know what this is. So in order to get that, we need to use implicit differentiation somehow so that we can have h prime, so we can find what dH dt is. But then what are we implicitly deriving? We have no formulas in front of us right now, right? So what we're really looking at is the volume of this figure. If we can get an equation for the volume of this figure, then we can derive the equation of the volume with respect to time. Then hopefully we'll be able to plug some things in. Okay, so the volume of any figure, any three-dimensional figure, would be the area of a two-dimensional base. So we got a triangle here. I can find the area of that base. But I want to have a generic formula first. That way, if I was to plug in 3, 1/2 times 3 times 4, and then multiply it by, what they're calling the length of the entire thing, that would be the volume if the entire thing was filled up. Right now I'm trying to come up with an equation that's the volume of the figure depending on the parameters, depending on the height, depending on the base, etc., etc. Okay? So the volume of this figure is going to be the area of this two-dimensional base, which is generically we would say that it's W times, this is what they're calling H because they're saying it's 4 centimeters, so W times H. So that's the area of this two-dimensional base. So to make it a volume, to make it like a three-dimensional area, you need to multiply by whatever the length is. But the length is going to always be 10 in this one. Okay. The width and the height are variables in this problem because depending on how high we are, the width will change, right? Depending on where we are with respect to time, the height keeps changing. Right now, this is the volume. This is what we'd use to calculate the volume. So the width and the height change depending on where we are in this filling up process. The one thing that does not change is the length of the entire thing. So normally we'd put in a 10 for the length, but we're going to put, normally we put in L for length if it was a variable, but since it's constantly 10, we can just plug in a 10 in here. The length isn't really a variable in this problem. Okay, so that's kind of a tricky point. So just to recap, the volume of this right triangular prism would be 1/2 times width times height times length. 1/2 times the area of the two-dimensional base times the length. But since the length isn't a variable in this problem, since it's always 10, we can just plug in 10, and that's going to save us a lot of trouble because then we have one less variable to work with. That's not always the case in some problems. Sometimes the width, the height, and the length all vary depending on what's going on with the filling process, and you'd have to use the product rule of 3 variables. Okay, so this is the volume. This is the volume of the water. Now, we want to know something about the rate of change of the height, so that means we need a derivative. So let's take the derivative using implicit differentiation of both sides of the equation. So the derivative of the volume with respect to time, we're just going to symbolize with v prime. Now, taking a derivative of this thing with respect to time, here, and this is, just clean that up, 1/2 times 10 makes 5. That's 2 different functions of time. 5w is some sort of function with respect to time. We just don't know what it is. H, something that could be implicitly defined as a function with respect to time. We don't know what they are, so we have to use implicit differentiation in the product rule. The derivative of 5w with respect to time is 5w prime. And then h is kept the same in the product rule. Derivative of the first function times the second function is kept the same. Plus the second function kept the same times the derivative of, sorry, I said that wrong. The first function kept the same times the derivative of the second function. So there is a derivative, and now we have that h prime that we're looking for. We want to get this by itself. So we got to find some information to plug in. They tell us the volume is positive 1 meter cubed, so we can put in a 1 for the rate of change of the volume. Because it's, sorry, I should say specifically, it's increasing at a rate of 1 meter cubed per minute. So 1 goes in for v prime. W prime, they don't tell us how fast the width is changing. So right now, we're going to have to leave that as W prime. The height of the water, length 10, the height, right when the water is 3 meters deep. Right now, the height is 3, so we can plug in a 3 in here. The width at this point in time is something we don't know. Right now they're saying the water is 3 meters deep, but we don't know the width. We could do some triangle stuff to figure that out though here, and I'm going to move this off to the side because it got kind of blocked by the picture. That's what it looked like when we plugged in all the information we directly know. But maybe we can find out, let me see, 3 for the height. We don't know the area. There's got to be a way to find out the width. Because right now we're trying to solve for h prime. We have 3 variables in one equation, so we don't have enough information to solve. But what we can do is we can use the fact that this triangle that represents the base for the figure of the water is a similar triangle to the bigger triangle up here. So if we call this side length W sub 1 because it corresponds with this W, then we can set up a ratio. Because similar triangles, the ratios of the corresponding sides should be the same. So the big triangle's width divided by the little triangle's width. That should equal the big triangle's height, like this. So the big triangle's height divided by the little triangle's height. The order matters there, right? This is enough information to help us find this W that we're looking for. Because we know the big triangle's height, that's drawn in red here, the width, they tell us, is 3. And then the big triangle's height, they tell us, is 4. And then we also know what the little triangle's height is going to be. We know what h sub 1 is because they said here at the point where we're interested in for finding the volume of the water, the little height is 3. So h sub 1 is 3. So we can plug all that information into this equation that we got from the fact that they're similar triangles. 3 in for W. W sub 1 is the thing we're trying to solve for. The height is 4 of the bigger triangle. The height is 3 for the little triangle. So if you solve that equation for W sub 1, this is 9 equals 4W. So that's 9 over 4. So now we have W sub 1. We can go back and plug it in over here, but I should be more specific with the notation, so this is my fault. We're making a volume equation for the water, right? So if this is an equation for the volume of the water, then this is W sub 1 here. And so is this. This is the rate of change of the width of the water. I think that's it. My sentence made it sound like there's going to be more there. So we have W sub 1 now. We know what the width is when the height of the water is 3, but we need to know the rate of change of the water for this triangle. And we can actually get that from this equation here that we just created, right? We want to just differentiate both sides. The width of the entire thing and the height of the entire thing aren't changing. Those are constantly going to be 3 for the width, and the height is 4. And now we know at this instant h sub 1 is going to be 3. But h sub 1 is going to be 3 at this instant. But if we were to plug that in, that's not going to give us the rate of change of the width, right? If you try to take a derivative of both sides, you're going to get 0 because at that instant, the width is a particular value when h is 3. We want a generic equation for W sub 1 prime. So if we just multiply h sub 1 and W sub 1 to both sides, just to make it easier to look at before we differentiate. Now we can take a derivative of both sides implicitly with respect to time. So this is 3 h sub 1 prime equals 4 W sub 1 prime. Because we don't know what they are as a function of time. So 3 h sub 1 prime and then 4wh sub 1 prime. So solving a little bit more to get w sub 1 by itself. W sub 1 prime is going to be 3h sub 1 prime over 4. So with that information, now we're able to algebraically solve this volume equation for h sub prime, which was our goal in the first place. So for w sub 1 prime, we found out in terms of h sub 1 prime, it's 3h sub 1 prime over 4. And then over here, this is 5 times 9/4 h sub prime. It's a solvable equation because there's only one type of variable, right? H sub 1 prime. Almost there. Once you do a couple of these problems, I know it looks intimidating and you probably weren't able to follow everything that's going on, but rest assured, once you do a few of these problems and watch it, follow along with me in some videos, you'll get to see the general idea and you'll start getting the trick of the whole problem. Similar triangles is probably going to come up a lot in Newton like I just did here. That's usually the key that unlocks it. But okay, we're trying to get h sub prime by itself, so that's 15 over 4 h prime. Oh wait, I forgot the 3 over here. That's 9 over 4, so it's 45 h prime, h sub 1 prime I should say, over 4. Plus 45 over 4 h sub 1 prime. Oh, that's going to come out nice. That's 90 over 4. And so if we get h sub 1 prime by itself, then that's 4 over 90. So it's positive. That means the height is increasing, which makes sense because we're filling it up. It's increasing by 4 over 90 meters per minute. So the height is going up. This part right here is going up by 4 over 90, or in other words, if I simplify this, 2 divided by 45 meters per minute. This is actually my second attempt making the video for this question. I got 10 minutes into it, and I found out I swapped my 5 and my 6. So right at the beginning, messed everything up. So just be careful with when you plug your numbers in. So we have a cone. That's a three-dimensional shape, right? So just careful, the picture is a cross-section. And we're filling up the cone with some water. Actually, we're draining cone, so we're losing water. The height is going down. Just like in the last problem, as the height goes down, then this radius is going to change. Okay, so the volume of the cone is where we'd probably want to start. The volume of any three-dimensional shape is the area of the base, so pi r squared because it's a circle for a base. And then you multiply by how far that base goes. This is our circular base, and it goes 6 in distance. So the variable for that, I think they're calling it the height of the cone. Okay, but because it's coming to a point, we also need to multiply by 1/3. Okay. So that's the volume of the cone. The question is asking for what is the rate that the height of the funnel is changing. So they want to know what h prime is. In order to do that, we need to use implicit differentiation. Before I do that, though, I'm going to put the 1/3 up front so I don't lose it. So take a derivative of everything with respect to time. The derivative of v with respect to time, we don't know what it is, so we call it v prime. And then the derivative of this function times the second function kept the same because we need the product rule. So it's 2/3 pi r times r prime times h. Okay, the derivative of this is 2/3 pi r, but then we need r prime because of implicit differentiation, the derivative of the innermost function. It's both the implicit differentiation and the chain rule. So the derivative of this with respect to time is r prime. So we chain it on with multiplication. Okay, but it's the product rule. We took the derivative of this times this kept the same. Now we need the derivative of this times this kept the same. Okay, so in order to solve for what we're looking for h prime, then we need to know what v prime is. And they tell us that it's decreasing, so it's negative. Oh, and actually, just a quick note, the answer says that we need it in exact form. That means they want it as a fraction. So instead of writing 0.8, I'm going to write negative 4/5. That way I keep it in fraction form. So we need to know what the volume is. We need to know what R is. We need to know what everything other than H prime is. And they don't tell us what the radius is at 4 feet, but I'll show you how we can find that. We need to also know what R prime is, which we don't know. They don't tell us how fast the radius is changing. And we need to know what H is. And this one they do tell us. The height is 4 feet when we're looking to solve. Okay, once we have all those, we can plug them into this volume equation that we can solve. And so where are we going to get R and R prime from? Well, it's from the similar triangles that we can do again. Okay, just like we did in the last question. So one thing we can, the two triangles we can look at are this triangle I've drawn in black, and then I'll use blue for the water triangle. They're similar triangles because one triangle is perfectly inscribed in the other triangle. And what we can say about the big triangle is that the big radius, this thing here, divided by the smaller radius, that should equal the big height divided by the smaller height. Right? The ratio of the corresponding sides should equal each other in similar triangles. And now we can plug in the particular information we have. We have that the big radius is 5. Don't know what the smaller radius is. That's what we're trying to solve for. Okay, what's the radius at this point in time? The big height is 6, and the smaller height, the h sub 1, is 4. Right? The height they give us for this water is 4. And so we can solve that equation real quick for r sub 1. That's 3/2. I'm trying to do that in my head, but I've done too many videos in a row, I think. So let me write it out. Multiply r sub 1 to both sides, so that's 3/2. Multiply that to both, so we're going to get r sub 1 is 10 over 3. Let me just double check that I have that right, because if I don't, I'm going to have to do this video a third time. So that's 60 over 12. Yep, that's right. Okay, so that's we could call it r sub 1, the radius for this particular instance in time. Now we need r prime, and again we can get that from this similar triangles ratio. Okay, we know some particular values, and we know that the radius of the entire big triangle is never going to change. That is always 5. And the height of the big triangle is 6. So if we rearrange that equation, get 5h sub 1 equals 6r sub 1. And we're trying to find out what r prime is. So if I differentiate both sides with respect to time, implicit differentiation tells us that this is the derivative. And divide 6 from both sides, so we get 5, 6 for r prime. 5, 6 h sub 1 prime. It's okay that it's in terms of h sub 1, even though the other ones are just plain old numbers, because we want to solve for h prime, right? We have h prime here. So that's something we can solve for. We've got everything we need to plug in. Now it's just algebra. Plug in negative 4/5 in for the rate of change of the volume. I had to back up the video because I got down to the end and I realized I plugged something in wrong. So negative 4/5 for the rate of change of the volume. The radius is 10/3. R prime is 5, 6. H sub 1 prime. And then H is 4. That's what I missed last time. I just missed one number 4. R squared, so that's 10/3 squared. And H prime, that's the variable we're trying to solve for. Alright, so that's just what we have to finish simplifying. So we multiply straight across the numerator. 2 times 10 makes 20. 20 times 5 makes 100. And I'll put the pi in the numerator. Times 4, so that makes 400. Pi in the numerator. 3 times 3 makes 9. 9 times 6 makes 54. This is all h sub 1 prime. And then we have 100 pi 9 times 3 makes 27 h sub 1 prime. So those are those are like terms, so we just need common denominators. So that makes 600 pi over 54 h sub 1 prime. So we just need to multiply by the reciprocal to finish getting our answer. So if we do that, 600 divided by 4, that makes 150. So 150 times 5 is 750 pi in the denominator, 54 in the numerator. Top and the bottom can be divided by 6. That's negative. Can't forget my negative sign. So that gives us negative 9 over 125 and pi in the denominator there.